Okay, so let's talk through a couple of key weaknesses with the simple calorimeter on the left. So in the bomb calorimeter on the right, the reaction, the combustion that's taking place, is completely surrounded by water. Therefore, as the heat is being released by the reaction, it essentially has no place to go but into the water that is completely surrounding it, even underneath it. So in case there's heat transferring that way. So the water is basically completely surrounding it. That means the water is going to maximize all the heat that it can catch coming out of that fire. To compare over here, yeah, a lot of the heat will leave the fire and will travel upwards. But other heat will be going off to the sides. And so because of how this is set up, where the container of water is just right above the fire and not completely surrounding it, you're going to have a lot of heat loss to the surroundings that is not the water. So this has to do with, a lack of insulation around the flame and just the location of the water. It's not completely surrounding the flame, and so that means that energy is lost to the surroundings. It doesn't go into the water at all. And so there's a whole bunch of heat that's not going into the water. That means that not all of the heat is causing a temperature increase. And so if the temperature increase is smaller than it theoretically should be, if all of the energy had gone into the water, the temperature would go up by much more. So the temperature change is smaller, and a smaller delta T mathematically leads to a smaller value for Q, the energy transferred value, and it leads to a smaller specific energy value. So if specific energy values are lower than the literature values, then this is probably one key reason why that is. Okay, another thing about the bomb calorimeter is it is pumping in oxygen. So why is that important? Well, we know that oxygen is one of the key reactants for combustion. And so the bomb calorimeter is designed to allow for complete combustion. Complete combustion involves forming carbon dioxide and water, which means we're making as many bonds as possible to oxygen, and so we are releasing as much energy as possible. Over in the setup on the right, even though there's plenty of oxygen in the room, that oxygen is not fully mixed in with the fuel at the point of combustion, and therefore there's a certain amount of incomplete combustion that's going to take place. Now, the evidence for incomplete combustion is the wavy yellow flame, smoke, and also soot collecting on the underside of a calorimeter. So there's lots of different signs that you could look for in observations. The incomplete combustion releases less energy than complete combustion. You've got fewer bonds being formed, which is where that energy release comes from. And if you release less energy, once again, you're going to have a smaller delta T, and a smaller delta T than you should is also going to mean that your specific energy value is smaller as well. So another reason why your value might be lower is because there's some amount of incomplete combustion happening. Okay, and the last thing is we can see that, well, the last major thing, although there's still a few things, but we can see in this one, the water is completely surrounded and insulated. So that's going to trap heat in. So as the water warms, heat's going to leave the water, but it will get sort of reflected back in, and it will stay inside the bomb calorimeter because there's this insulating layer on the outside. That's a lot different than this setup, where when the water gets warm, then the heat can just leave the water. So as soon as the water gets hot, it starts losing heat to the surroundings. And so there's a certain amount of heat loss that takes place due to a lack of insulation. So let's see. Let's take away lack of insulation from that first weakness, because that's a little different. I think lack of insulation around the water is another weakness that we could identify. Therefore, there's additional energy loss from the water, and once again, smaller delta T and smaller specific energy. Okay. You could also highlight other things like how the heat, some of it's going into the container itself, and that's not necessarily accounted for in the calculations. Things like that. But the main three would be the heat that never goes into the water, the heat that is lost from the water, and the incomplete combustion that takes place because of the oxygen not being fully mixed in with the fuel. So those are some key experimental weaknesses in simple calorimetry.